In this video I will talk about smart signal processing for massive MIMO in 5G and beyond. My name is Emil Björnsson, I'm an associate professor at Linköping University. So this is going to be about cellular communications and ways that we can evolve it in 5G and in future networks beyond that. So it's a cellular network where you divide an area into a number of cells and you are serving the users within each of these cells in a semi-independent fashion. And in a network like this, the data throughput that we can deliver in bits per second per square kilometer depends on three different factors. There is the frequency spectrum, there is the spectral efficiency measured in bits per second per hertz per cell, and there is the cell size being number of square kilometers per cell. And if you multiply and divide these units together, you get bits per second per square kilometer, which is the unit for area throughput. And if we want to improve the area throughput in future network, we have these three different factors to play around with. And it turns out that going forward, we won't just have one type of way of making this area throughput high. We will have a network with two different tiers. There will be a hotspot tier, where you put out small base stations that cover a small region. So you can have a high cell density, small cell size, and you have short range per cell. And in these cases, since you are anyway targeting a short range, you can use spectrum that only works well in short ranges, such as the millimeter wave spectrum, where you have wide bandwidth available for future wireless networks. And in this case, the spectral efficiency might not be so important because you have a lot of spectrum, you have a small cell size, so these two will contribute to high throughput. But that type of approach won't be able to give us wide area coverage. You will need a coverage tier still in networks that provides coverage over a large area, so wherever you are, you will at least have coverage by this tier, but if you are lucky, you also will have the hotspot tier there. And in particular, outdoor to indoor coverage will be important. We put base station outdoors and cover you as a user wherever you are, indoor, in the basement, or and a place where there is not a hotspot. And therefore you need to operate at lower frequencies, where there is not so much frequency spectrum. And the cell size, you want it to be large to cover a large area, and put base station at elevated locations so you oversee all the obstacles. And that is the reason why the spectral efficiency is the key in order to improve the area throughput in the coverage tier. So in the future, you will have a network with base stations in the coverage tier and small hotspots here and there, and depending on where you are, you will connect to one of these tiers. In this talk, I will talk in particular about the coverage tier, and one reason is that even if there's a lot of talk about millimeter wave spectrum for 5G applications, the new thing will be that it is in the 3 GHz band where 5G will be mostly used, even if millimeter wave is another alternative as well. So what about the spectral efficiency then in the coverage tier? What we are seeing today is that these are locations where there are base stations, and if you are, as a user, at the position close to a base station, you can get a high spectral efficiency in bits per second per hertz in that cell. And as soon as you move away and you are somewhere in between two different base stations, you will have a spectral efficiency that's very much lower because there is both a signal loss and a particular interference from the neighboring base station. What we would like to get to is a case where, well, we will still have some kind of propagation loss. The further you are away from the base station, the lower the signal power that you receive is going to be. But if you can deal with the interference problem, you will still have a fairly high spectral efficiency wherever you are in the cell. So in order to achieve that, we would like to somehow provide you with a stronger signal and the same interference level, or potentially the same signal but lower interference level. And the conventional way of trying to give you higher signal power is to have a high gain antenna that is directive. So instead of just radiating the energy in any direction, you radiate it in where you think that most of the users are. So this is a typical cellular antenna with a fixed beam into the center of the cell, maybe it gives you 16 dBi, 16 decibels stronger signals than as if this will be an antenna that is just sending out isotropical in all directions. And some users that happen to be in the cell center or right in front of it will be lucky. They will get an SNR that is improved by these 16 decibels. So the signal-to-noise ratio will be much better for these users. And they don't really need any improvements. These are the people that were in the center of these high peaks on the previous slide. However, the unlucky users will exist. These are users here that are blocked by different buildings, or maybe they are even inside a building. And they will not benefit from these 16 dBi, because that is only in this fixed direction over here. In order to reach them with a strong signal, what we need to do is some kind of thing that is called adaptive beamforming, where this beam is not in a fixed way towards its users, but you can also redirect it so that it bounces different objects, finds its way to these users here, which is more complicated because you don't know exactly where they are. These just happen to be lucky being in the center of the cell. So how can we achieve that? Well, this is how the cellular technology has been looking like for a long time. You have one antenna in the cell, and this is called a sector antenna because it covers a cell sector. If you look inside, it contains maybe 8 different elements. Each of them have its own gain of, for example, 7 dBi. And then when you add that together for 8 antennas, if you happen to be in the center of the beam that it creates, then you will get 16 dBi. So 7 plus 9 for these 8 elements. And there's only one transceiver chain connected to each because this is creating one fixed beam. The first way of going forward is to put multiple of these columns next to each other, and each one of them can also have dual polarization. So here we have 4 columns and 2 polarization for each of them, so there's 8 antennas of the similar kind as before. And this is a classical antenna array. So there is actually 64 different elements, 32 per polarization, but they only are mapped to 8 different transceiver chains, creating 8 different antennas. And in that way, since one antenna is one column here with one polarization, we can create different adaptive beams in the horizontal direction by varying how you send the signals from these different columns. And if you want to go even further, up to 64 antennas, which you have seen now in the first deployments in LTE advanced with 64 antennas, you have arrays of this kind, where you have actually the same form factor as before, same 64 elements, but each one of them is now connected to one transceiver chain. So there's 64 elements, 64 transceiver chains, meaning 64 antennas. And since you now can control the direction not only horizontally, but also how you put together the signals to each of the vertical elements, you can now direct beams in any direction you like, horizontally, vertically, and that's what we call 3D beamforming. And what is then important to remember here is that the number of antennas is always equal to the number of transceiver chains when you're looking at an antenna like this. They might have the same number of radiating elements, but it's the number of transceiver chains that matters. And even when you go to more antennas, it doesn't mean that form factor needs to be larger. It's just that we can take the same radiating elements and connect them to a larger number of transceiver chains. And when you have this flexibility of controlling all of the radiating elements, having 64 of them, you can not only send a signal directed towards one user, but you can do something called spatial multiplexing. And this is something that's been around for a long time. Earlier it was called space division multiple access, and people thought that to talk about it already in the 1980s for the uplink. In a case where many users are sending signals at the same time and frequency, and the base station equipped with different numbers of antennas can use these antennas to distinguish between the users. And we will let the users be k of them, and the number of antennas at the base station be m. That's a number that we use in this presentation a lot. In the downlink, that was something that appeared a few years later in the 1990s. Transmit beamforming of this adaptive kind I've been describing, and if you direct it towards one user in one direction, you can direct towards another user in another direction at the same time. So with M antennas and K users, you can send one directed beam for each one of them. And typically when people conceive the space division multiple access approach, they had the ideas that the number of antennas and number of users should be approximately the same. But then there came the massive MIMO approach. MIMO standing for multiple input, multiple output. So that's the multiple antennas at one side and multiple antennas at the other side. And Thomas Mercetta was the inventor of this idea, which based on having a massive number of antennas. So the number of antennas, M here goes to infinity, while K was just a fixed number. And this is something that he did in a paper called Non-Cooperative Cellular Wireless with Unlimited Number of Base Station Antennas. And it came out in 2010, and for years people were thinking, well, you can't have an unlimited number of antennas, so this doesn't really make sense. And then they started to realize that actually the phenomena that Mercetta was demonstrating very nicely in this paper is something that you can also utilize in practice. So let's look at these basic things that he observed. We look at an uplink scenario where we have two different users, user 1 and user 2, that send signals S1 and S2 to the base station. And these signals are propagating through channels described by vectors H1 and H2. The base station have M antennas, so therefore each of these vector channels are just M-dimensional vectors. Let's assume that they are generated randomly with zero mean and unit variance for each element. Then the received signal at the base station will be the first user's channel times its signal plus the second user's channel plus its signal plus noise. And this noise I assume to be complex, normal, distributed unit variance, just for simplicity. The base station then receives this combination of the signal, and it likes to distinguish between S1 and S2. Let's focus on S1. How do we detect S1? Well, we select a filter, spatial filter, that put together the signals over the M antennas in such a way that we will get something similar to S1. And Mercetta suggested to use what is called a matched filter, which is matched to the channel of the user interest. So we just take the channel H1, we normalize it with the number of antennas, 1 over M here, and we use that as a match filter. In the way that we take the received signal Y, we multiply it with V1 here, creating an inner product, and in that way we just get V1 multiplied with the first term, with the second term, and the third term, like this. And then you can use something called the law of large numbers, which says that this type of expression, the inner product between the channel itself divided with the number of antennas, goes to its variance, which is 1 times S1. And the other terms here with the law of large numbers, one can show that these will just converge when you have very many antennas to 0. Meaning that the output of this match filtering is just the signal of interest. So the conclusion is that the noise interference disappears when you have very many antennas, so you get an interference and noise-free communication, and that can bring us just any communication performance that we like. However, in reality, we don't have an infinite number of antennas. So let's talk about the canonical form of massive MIMO, which Mercetta didn't define himself in his seminal paper, but something that you, for example, can find in my book, Massive MIMO Networks. We say that massive MIMO system is a cellular network with many antennas, M per base station. Say that M should be greater or equal to 64. And it is assigned to spatial multiplex many users per cell. For example, it should support at least 8 users. And the key here is that the antenna to user ratio, M over K, is greater than 1. In this case, it's 8, for example. But of course, it will vary over time, depending on how many users there are in the system at that particular moment. And we also use linear transmit precoding and receive combining in the transmission in the downlink and the reception in the uplink. And these are schemes that I will talk about in this presentation. So how do we operate a massive MIMO system in the canonical form? Well, it's based on something called TDD, time division duplex, where you take the time frequency resources and chop it up into frames. And we do this keeping in mind that channels are changing with time and frequency. But we can create something that is based on the coherence block. In the coherence block, that is the time interval, coherence time, TC, that the channel is approximately constant. And the coherence bandwidth, BC, which is the frequency part, where you also can say that the channel is approximately frequency flat, so it's only described by one scalar. So we have a constant scalar value between each antenna pair in a coherence block. And the number of channel uses or symbols that we can send over this coherence block or frame is the product of the coherence time and the coherence bandwidth, tau c. And depending on the propagation environment, you will have different numbers here, but typically between 100 and 10,000. And each frame is divided into an uplink part and a downlink part. That is where the time division duplex comes in. So we switch between uplink and downlink over time. And in the uplink, we need to send pilot signals, K, because we have K used in the cell, and these are unique signals that the different users in the cell are using in order for the base station to estimate them, and these signals are deterministic, so you know them in advance, and therefore you can look at them, the received signal, and guess what the channels are. And then the rest of the uplink is used for data, and the downlink is used for data as well. So tau c minus k symbols, that is the amount of payload data that you can put in each frame, and you can divide them between uplink and downlink in whatever way you like. And these k signals are also reused in every cell in the cellular network. And we now see that there are a number of different signal processing schemes that needs to be used. We need to use some kind of scheme for the channel estimation based on the pilots, and we need to use some kind of scheme for the pre-coding when we transmit and the receive combining when we receive something at the base station. And there in the literature is a list of different methods that can be used. For channel estimation, there is least square, LS, minimum mean squared error, or MMSE, and also something called element-wise MMSE, which is like MMSE, but you take one element at a time, ignoring any type of correlation between the different things you want to estimate. For pre-coding, there is the match filtering that I mentioned. There is zero forcing, which is a very popular method of cancelling interference. There is the regularized zero forcing, and there is MMSE processing, and you can make the list longer, and that also applies to channel estimation. There are many different schemes in the literature. The question is which one to choose. For some choices, your bits per second per hertz will be much better than the system of today, which might have 3 bits per second per hertz, but you might only be able to reach up to slightly above 20 bits per second per hertz per cell, while with other choices, you might go all the way up to almost 100 bits per second per hertz per cell. And this all depends on the choice that we have. Some choices are smart and would lead to performance like this, and some are just bad and will perform like this. However, in the beginning, we might still be sufficiently happy with the bad choices, but we need to know what are the good choices so we can implement them when they are needed, when we need to go all the way up here. So this talk will be about what are the smart signal processing schemes that we actually need to use. So the first claim I'm going to do is that match filtering is not optimal, even if Marchetta was using it to demonstrate some key properties when you have infinitely many antennas. And the first thing I will look at is an uplink example with a single cell. You have 10 users in the cell, you have a signal noise ratio of 15 decibel, and all the channels are IID Rayleigh fading. So they are independent elements, and each one of them have a Gaussian distribution. And here is the sum spectral efficiency of the 10 users, depending on what number of antennas that we're having. The black curve here is with match filtering, the red curve is with zero forcing. And we can see that there's a constant gap between them, and this gap will continue. You can actually compute an expression for it in closed form that tells us how large this gap is. But it will continue as we add more antennas. So in a single cell setup, match filtering is not optimal, zero forcing will always be better. If we instead go to a multi-cell setup where you have another cell, and this cell contains k users as well, and these users are using the same pilot, so user 1 in each cell uses the same pilot, user 2 uses the same pilot, and so on. That creates interference both in the pilot and the data transmissions, and Marchetta showed in his first paper that this creates an upper limit. And this is the upper limit that you can compute, and you will reach it when you have infinitely many antennas. Zero forcing and match filtering still have a large gap, meaning that if you are targeting a certain spectral efficiency, you can get away with much fewer antennas when you use zero forcing. But asymptotically, both of them will reach the same limit. But for any number of antennas, match filtering will not be the best choice. So therefore, I'm adding match filtering to my list of bad processing schemes. Zero forcing was better than match filtering, but it's still not a good method by itself. And to demonstrate that, let's create an uplink scenario. Here I have 4 base stations, and I have 2 users in every cell. They are located here in the shaded cell edge region, and I have Rayleigh fading with a little spatial correlation. So it's a model saying that the coefficients in each channel vector are correlated with each other in a way that describes the signals are actually coming from the base stations in a particular way. I've created a very mean system setup where the interference is strong. So the SNR within my cell is -6 decibels. And I have -6.7, a little bit less to the interfering channels in the other cells. Here I am showing match filtering, the blue curve, zero forcing and regular zero forcing performing essentially the same, and something called MMSE processing. And what you can see is that match filtering and zero forcing are converging to a limit, just as we saw on the previous slide, but the MMSE processing scheme has a performance that just goes upwards. And this is the number of antennas in logarithmic scale. So this linear scaling here means that the spectral efficiency with MMSE processing is growing as log of the number of antennas. And here we have spectral efficiency per user. So what this means is that to the list of bad processing schemes, we not only have match filtering, we also have zero forcing, and actually regularized zero forcing can be added here as well. And the fact that this goes upwards was something that people didn't really think was the case for a long time, but it was shown recently in our paper, Massive MIMO has a limited capacity. Let's now look at the point where we have 400 antennas with this gap. And here I have divided the received signal at the base station into different categories. The desired signal for a particular user, the interference that come from users with the same pilot, these are used in other cells, and interference that come from users with the same pilot, one in my own cell and one in each of the other cells. With match filtering, which is sort of ignoring the existing interference, we get the highest desired signal, but also a lot of interference, both from those with the same and with different pilots. Zero forcing suppresses interference between users in their own cell. And for that reason, the interference is going down here, but you see that the interference is still large from users using the same pilots in the other cell. And it goes down a little bit, and that's just because in order to reduce the interference from within the own cell, I need to sacrifice a little bit of my signal power, and the power then of this interference is also going down as a byproduct. MMSE processing cancels interference from wherever it comes from. It doesn't distinguish between users being in my cell or from another cell. In that way, it's able to bring down this interference from users with the same pilots by 10 decibel in this case here. And in order to do that, it sacrifices a bit of its received signal power, and it also is not putting the same emphasis on canceling interference from within my cell, because this was actually a dominating factor in terms of the interference. So the price to pay for doing MMSE processing or canceling interference is always that you go down in your desired signal power, but if you do it in the right way, you will still benefit in terms of signal to interference and noise ratio, because with the white scheme here you get much lower interference. The difference between the desired signal and the most strongly interfering signals is much larger here. So what makes MMSE processing smart? Let's here define HLJ as a matrix containing the channels of the users in cell L to base station J. So J is the index here of the base station, and here is user 1, 2, 3, and up to K in that cell, their channels, and here's the matrix that contains those ones. The match filter is just taking this matrix when J and L are the same, and it normalizes. This is what we showed before. You just take the channel of the user of interest and normalize it. And what this means is that you will form a signal beam directed towards where your desired user is, and you will do it without caring at all about where the other users are. So here is a user in the same cell, here is a user from another cell, and in this case, this beam, there is a main lobe of the beam focused towards the user, but there is always side lobes that are going in some other directions. In this case, it happened to be a side lobe directly on top of the same cell user, and also some interference towards the other cell user. Zero forcing, or regularized zero forcing, is trying to deal with interference that goes in the own cell, particularly for the same cell user here. And it does it by taking channel matrix from within the cell and multiply with the matrix that is trying to rotate these beams in a good way. And it does it by taking the inverse of a matrix containing the channel matrix itself, multiply with the Hermitian transpose plus an identity matrix. And this identity matrix can have a scalar here in front, which is a regularization factor. If you remove it, you can write it and this becomes zero forcing, which only tries to cancel interference. And what you see here is that this beam has been rotated a little bit, and that means that now you have much less interference. This side lobe here is missing the user. However, now you rotate the thing so that there is instead a side lobe towards the other cell users. And that is what MMSE processing is dealing with. Remembering that, okay, if I put in a channel here, this will help me to remove interference towards those channels. If I do the same thing, but I not only take my own cell channel here, but all of them, 1, 2, and so on up to L, then we will get MMSE processing. And in this case, I've rotated the beam in another way. There is still a user here being more or less in the main lobe, but now at the edges of it. And the side lobe here are not pointing towards either the same cell user or the other cell user. So that is what MMSE processing is doing. However, if you read Marcetta's book, Fundamentals of Massive MIMO, he's saying in one of the chapters that all known capacity lower bounds approach a finite limit when m goes to infinity, which seems to go against the result that we have seen that MMSE processing can do. And one of the issues here is that we don't know the channel matrix perfectly. We only know an estimate of it. And the same k-pilots are reused in every cell, and that creates something called pilot contamination. And with IID Rayleigh fading channels, the problem is that if you want to estimate the channels to another cell, my estimate will always be proportional to the estimate that I get for the users in my own cell. So user 1 in every cell will have the same channel estimate up to a scaling factor, user 2 will have the same estimate up to a scaling factor, and so on. That means that when I try to form this thing in my MMSE processing expression, channel matrix of all the channel times its Hermitian transpose, since each matrix here is the same after scaling factor, this is no different than just trying to put in one of the cells, my own cells matrix, and multiply with its Hermitian transpose, as we were doing the regularized zero forcing. So when you use your channel estimate in these cases, there is no reason why MMSE processing will be much better than regularized zero forcing. But this type of result is an artifact of using a particular simplistic channel model, namely IID Rayleigh fading. So this conclusion is based on IID Rayleigh fading, and it doesn't hold in any other cases because this proportionality won't appear in those cases. So why do I say that IID Rayleigh fading is a simplistic model? Well, it doesn't have all the properties that the real channel is going to have. For example, there's natural power variations between the different antennas when you look at the received signal from a user, and these are actually easy to estimate. You can use them in any real system. In a measurement paper from Lund University called Massive MIMO in Real Propagation Environments, do all antennas contribute equally? They showed that there were 4 to 7 decibel variations between the received signal for a user. So here is a line of sight user, and the received power varies along the antenna from 1 to 128. And for a non-line of sight user, you see similar variations. Now you have a lower power, but it's still variation. And if you would look at another user, it will also have the same type of behavior, but it will depend on where the user is and look differently. So every user have a power variation that is user specific, some kind of spatial signature of that user. In addition to that, there could be other types of spatial correlation that also says that the elements of my vectors are related to each other in terms of phases and things like that. If we mimic this random or these power variations in a random way, then this is the result we're going to get. Here is the spectral efficiency in the same setup as before. Here is the standard deviation of my random variations of the power. And these are random variations in decibel scale. We have MMSE processing, regularized zero forcing, and match filtering. And when you have no variations, these methods are all the same, but as soon as you introduce these changes, MMSE processing is growing much better than the other ones. The other ones are also benefiting from this type of spatial correlation, but it can't utilize it in the same way. How is MMSE processing utilizing it? Well, now the estimate of a channel to another cell is not proportional to the estimate within my own cell anymore. And that's what we're going to use. So, which channel estimators are we going to use? Let's compare some different choices. Let's do it in a bit more realistic setup. You have 16 cells, you have 100 antennas at the base station, 10 users randomly located per cell. And each cell have a certain size, they have base station in the middle, users are randomly located. And we have a wraparound here so that a cell here at the edge will still interfere with cells nearby in other directions. There are three different key methods that I mentioned before when it comes to channel estimation. There is the MMSE estimator that knows the channel statistics perfectly. There is the element-wise MMSE estimator that knows the power that you have on the average for every antenna and user pair, which are these variations that I showed in the previous slide. And then there is a least square estimator that have no idea about the channel statistics. Here is the sum spectral efficiency in the cell that you get with each of these choices with three methods: MMSE processing, regularized zero forcing, and match filtering. So what can we see here? Well, we need a smart estimator such as MMSE or element-wise MMSE if we're going to use MMSE processing for the uplink or the downlink transmission. Then we get much better performance here than both regularized zero forcing and match filtering. However, if we are going to go with the regularized zero forcing and match filtering, the difference between the red columns or the white columns is not large. It doesn't really matter much which of these estimators we are using. So least squares is okay if we use any of these bad signal processing schemes. So good schemes go together, bad schemes go together. So what are the conclusions then? Well, it's dangerous to extrapolate results that you obtain in one setup and think that they are going to be applicable in other setups. So this applies to going from single cell to multi-cell scenarios. For example, zero forcing is getting a lot of attention, and it's a good method in single cell scenarios. But as soon as you have multiple cells, there's no reason to not trying to cancel out interference from users that might have the same interfering level to you, but happen to be associated with another base station. So a smart signal processing scheme like MMSE processing for precoding and combining can cancel interference from wherever it comes. It cancels the strong interference and in a soft manner ignores the weaker interference. Also, observations based on simplistic channels are also misleading. So it's tractable to work with IID Rayleigh fading. You can get nice expressions, for example, but it leads to an overemphasis on pilot contamination. For example, match filtering is not asymptotically optimal in any practice scenario, but you can get that feeling by looking only on IID Rayleigh fading channels. A smart signal processing scheme needs to exploit spatial correlation, in particular these power variations that you will have between the antennas. Now you can ask, is any of these things I've been talking about really new? Interference rejection combining is a name of a method that people were suggesting already in the 90s. It was based on trying to distinguish between the desired signal and all types of interference from wherever it was, and just trying to suppress that one in different methods. And in a way, this MMSE processing that I've described here is just one implementation of classical interference rejection combining. It's just that people haven't explored until very recently how it behaves and how it changes things fundamentally in a massive MIMO system where you have many antennas. From this, I would like to finish up by defining what I call Massive MIMO 2.0. And this is the improved version of Massive MIMO that improves things far beyond what Marcetta was predicting in his first paper on the topic, where pile contamination appeared to be the fundamental limitation. So a Massive MIMO system in 2.0 should have at least 64 antennas, at least 8 users, should operate in TDD operation and exploit channel reciprocity, and exploit spatial correlation to estimated channels in an effective way, so we can estimate channels to use this also in other cells and use them to suppress interference. And we do that with the smart pre-coding and combining schemes like MMSE processing, and this can suppress all kinds of interference in the network. With that, I would like to thank you for watching this video. You can read more about Massive MIMO on the Massive MIMO blog, or you can watch other videos on my YouTube channel. You can find papers on my webpage and also code that reproduces results from many of my papers on GitHub. And finally, my book Massive MIMO Networks, Spectral, Energy and Hardware Efficiency, that I've written together with Jacob Hoydis and Luca Sanguinetti. This book is available for $99 in hardback color printed version, and you can also download a free PDF of it from MassiveMIMObook.com.